morning, everybody. It's a great pleasure to welcome Peter Ban, who is from Vigil's Research Center for Physics. He's their scientific advisor and deputy director of the Department of Theoretical Physics at the Institute of Particle and Nuclear Physics. He's interested in non-equilibrium thermodynamics, classical and relativistic fluids, but particularly now as a new road to foundations of quantum mechanics. And he's keen to discuss this with us afterwards. I'm going with him for lunch, so you're welcome to join if you want.
Everybody welcome.
He has several PhD degrees. I didn't get fully. There's something in applied physics,
Hungarian
physics, also on the work on non-equilibrium thermodynamics. Has also some awards like a gold level Montevid Research Medal, and he's a foreign member of academia, but I'm not sure I will pronounce it. Peloritamia de Pericolana, something like that. Okay, and today he will talk about a little bit of Bohmian mechanics. There will be no Hilbert spaces, as I understand, and giving some thermodynamical origin of, I guess, quantum mechanics. So, looking forward.
Thank you. I'm really glad to be here and tell you about quantum mechanics without any Hilbert space operators, which could be frightening, but probably, I hope, will be also interesting. And the title of the presentation is the Holographic Thermodynamic Road to Quantum Physics. And in particular, I will focus on an interesting property that I call holography. So the talk will start with an introduction that will be long. I will clarify some concepts. And then, actually, I speak about non-equilibrium thermodynamics and try to argue that it is a meaningful road toward understanding some quantum systems, at least. We don't go farther than Schrödinger equation, or maybe in a different point of view. And I will speak about fluids. The background is fluid mechanics, and I hope that it will be really interesting. Okay. So since 1992, when Bell was speaking about the 6 words of quantum mechanics, there are many, I think. And they are usually called interpretations. I don't like this word because interpretation means that you are inferior. You cannot go beyond the original. And my ambition is that to show that beyond the classical quantum mechanical systems, there is another world that is strongly and inherently connected. What I will not speak about that may be asked, of course, but not the subject of the presentation, is superfluid mechanics and superfluid universe, hydrodynamic quantum analogues like the pilot wave hydrodynamics. I don't speak about holographic hydrodynamics that's coming from string theory, all connected subjects. And I don't speak about quantum thermodynamics either. And my talk may be best understood when you are familiar with Bohmian mechanics. Actually, this will be an argument that what is Bohmian mechanics and how is it connected to fluids. And I can identify, I say that could be identified some problems that I'm aware of Bohmian mechanics, like what could be the predictions beyond quantum mechanics, the origin of the Bohm potential, how to create spins, I mean, for example, empty waves and representation of fermions, and of course the transition of quantum classical boundary and the measurement problem, and so on and so on. But I'm interested also that whether you can tell me some benchmarks where that kind of approach could be validated. So not only maybe solving the problems, I claim that the blue marked points are somehow addressed in this talk. So the origin of Bohm potential, for example, in a sense. And I'm very aware that the treatment of spin could be an important benchmark in not only in the framework of quantum Bohmian representation, but also in fluid mechanics, especially in relativistic fluid mechanics in general. But please, if you want to give me a feedback, and I would like that some feedback could arrive, that would be most interesting for me if you give your opinion why this approach is wrong. What is your scientific opinion? How could you be convinced that it is somehow useful and interesting? And finally, all these things are more or less treated in detail in the publication below. Okay, first concept, local, non-local, and weakly non-local. Emphasis is on weakly non-local, and let me clarify some background. So we can distinguish between locality in space-time and locality in time somehow, especially in non-relativistic case. And locality in space means local fields and local field equations. For example, the Poisson equation of gravity is a local field equation. And a strong locality, non-locality, is sometimes considered as a dependence on some integrated areas of the space, or introducing direct non-locality on the basic fields, like in the Liouville equation, a two-particle representation. And weak non-locality, which is the subject of this talk, is that when we have a field equation and we want to somehow extend it, introducing higher order derivatives in the equation, and this is you will see what I mean about that, and that will be a crucial point in the further understanding, especially like examples like gradient fluids or Horndeski gravity, if anybody knows about. And one may distinguish locality in time, which is memory. Local processes in time, for example, Markov processes. And in thermodynamics, the principle of fading memory introduces some history integrals directly into the equations to be solved. So this is a strong non-locality in time. And multi-temporal fields, I think it's somehow science fiction. I don't know a good example in physics, maybe you know. But weak non-locality in time is when you introduce higher order time derivatives in the field equations. For example, extend a parabolic equation, a first order in time, to a second order, introducing a second order time derivative. It introduces delay and inertia effect. So mechanics, inertia is a memory effect, a local, weakly non-local extension of a first order equation in time. So when you have this impression about locality, let's speak about holography. I will distinguish three kinds of concepts. First, the holography is the optical holography. You know well that this is due to Denis Gabor. And essentially, it is used as an analogy here. So reproduction of three-dimensional information from two-dimensional projections. Of course, it is available not only in optics, but one can reconstruct ambisonic sound, so the whole sound picture in a room or in a music performance. What is important that you need something, some requirement about the field equations behind. And that is actually motivated the holography concept in quantum field theories, which originated in black hole thermodynamics. And the reason and the motivation is that for black holes, the entropy is a surface. So it's the area of the black hole, let's say, not really. Anyway, so surface concepts, so so it is a differential geometric concept. It's not really a particular part of the, or four-dimensional space-time. But anyway, the surface entropy is responsible for a three-dimensional information, and somehow abstracted in string theory. became an expectation in quantum gravity and somehow property that we expect from the most developed field theories that we use. And it is embodied in the ADS, anti-de Sitter quantum field theory correspondence, which is still a correspondence. And of course, connected to entanglement as a particular representation of the quantum representation of the entropy, because they looking for some statistical physical background, Unruh effect. And I emphasize here that there is thermodynamics there as well, not only for black holes, and for example, the emergent gravity of Verlinde. However, for that, the motivation is that one can represent the degrees of freedom of the particular physical system in a two-dimensional way, and that is describes a three-dimensional information. However, what I will speak about it's not that, not exactly, also related, but I call it classical holography, and it is related to the balance of momentum. The balance of momentum in a Galilean relativistic or non-relativistic space is expresses a balance in the sense that in a global form where the time derivative of momentum is due to surface terms and bulk terms inside a particular space region. In local form, it can be expressed in this way, where P, the pressure tensor, represents the current density on the surface on an arbitrary part of the space. And here I introduce the co-moving or substantial derivative, which can be written in this way for an arbitrary quantity. The velocity field is so the acceleration is understood when you're moving together with the fluid. And also, it was introduced that P here is the conductive derivative. The pressure, that moves, considered, the surface current density of the momentum that moves together with the fluid. So this representation, or let's say reference frame point of view, is very important in fluid mechanics, because there we need to define what is moving together the fluid and what does it look like from the point of view of the external laboratory frame observer. And what is interesting, that for example, in case of gravity, simply Newtonian gravity, the bulk force, the gravitational force, actually can be surface force at the same time. So, because the gradient of the gravitational potential becomes a divergence of a particular field tensor, 3 tensor, it can be written this way, it's easy calculation. Therefore, for gravity, surface and bulk forces are equivalent. So you can take any, let's say, surface around the gravitating object, and then you can calculate the forces for a test particle inside. In this sense, gravity is holographic. Three-dimensional information is encoded in a two-dimensional surface or any two-dimensional surface. And if you look at the momentum balance, if you do this transformation, divide by rho, you get this equation, which looks like a local Newtonian equation. And therefore, it means that for gravity, the fluid actually can be represented or understood as a particle. But how? And that is a point. So if phi is fixed, then it's really a, let's say, equation of motion for the test particle. Or if you introduce some integrating screens, then a particular mass of fluid, like the Earth itself, can be represented by a point mass. This is at the background. However, it is somehow introduced in a different way. And you also may understood that this is like a pilot wave theory, in the sense that actually this field here, or let's say potential, is governed by a system of partial differential equation at the background. So its similarity is maybe interesting, and it is not exotic property of gravity. It is actually well known in case of Euler fluids, where the so-called Friedmann form of the Euler fluid momentum balance shows that the gradient of the thermostatic pressure is the rho times the gradient of the chemical potential. So a homothermal, and also the gradient of temperature appears here. For a homothermal system, I mean with constant temperature, homogeneous temperature, then the chemical potential actually is a mechanical potential as well. This is valid for any fluids. This follows from thermodynamic principles. And therefore, I defined this classical holographic property in this way. So if there is a pressure whose divergence is a rho times some gradient of something else, then it will be called the fluid holographic, classically holographic, to distinguish between the others. And of course, this is a material property or field property, a property of the field equations. And the question is that what is the reason of this property and how is it related to, for example, quantum mechanics? Some, maybe to make you remember to some calculations of how hydrodynamic is connected to the Schrödinger equation. It is easy. You perform a so-called Madelung transformation that was established, I think, some months after Schrödinger published his famous equation. And if you separate the imaginary and real parts, then you can realize that one of them, the imaginary part, is actually a continuity equation. Rho is the probability density here, and the other part is actually a Bernoulli equation for a classical rotational free fluid, because the velocity field is assumed to have a potential, and the potential is actually the velocity potential is the phase, related to the phase of the system. And the gradient of the Bernoulli equation became the previously mentioned form of, let's say, Newtonian form of the equation. And if UQ is actually the Bohm potential, then we get the Bohmian mechanics. That is maybe the simplest way to get it. And also, Bohmian mechanics, it is holographic, so it can be transformed to a particular so this gradient can be expressed in a particular, with the help of the particular pressure tensor. The question is, why? My point is that the previous way of thinking was considered usually as an analogy. From quantum mechanics, we can get maybe superfluids and also capillary fluids, because the Bohm potential is a particular capillary fluid. We will see why again, so I don't explain. So anyway, there is an analogy between quantum mechanics and fluids, and this is very strange, and we don't really care about. For a long time ago, it was rejected as a valid theory of fluids, or valid theory that related to quantum mechanics. My argument is the following, that actually if we start from the opposite direction, from capillary fluids, then we can clearly distinguish the conditions to get superfluids, and from the superfluids to arrive some quantum mechanics. And this is analogy, but this is a kind of deduction, so with clear conditions. And actually, the second law of thermodynamics will be responsible for classical holography. So holography follows from the second law. This is my argument. And also, if I introduce another property, which is additivity, actually, then we get Bohm potential. Why and how? To understand that, we need to I need to explain some parts of non-equilibrium thermodynamics. The most important point here, that thermodynamics is not statistical physics. it is connected, but thermodynamics is what is not what is universal in the whole material science. For example, the concept of absolute temperature is independent. So there is an argument in thermodynamics that the temperature is somehow universal, and this is called absolute, not the existence of zero or not, independent of the material. So I have a temperature of a light or the desk or the computer with very different material structure, and it is the same concept. That kind of absoluteness cannot be really expressed in statistical physics, because statistical physics by definition is structure dependent. And actually, the unknown microstructure, sometimes like the desk, it is very complicated, could be described properly, but we use highly idle models. So I just say some examples. So for example, we neglect the internal self effect of the fields, and of course we don't use ball-like particles and so on. So we should have some information from the microstructure, and then we can somehow justify the thermodynamic principles. But general principles cannot be proved, only demonstrated. Therefore, so this is an idea, the basic difference of, let's say, conceptual difference of a thermodynamic way of thinking and statistical way of thinking. And thermodynamics actually separates from the universal to the statistical or particular information. At least this is my way of introducing here non-equilibrium thermodynamics. What is important that we need to use clear mathematics and clear understanding of the role of space-time and the second law, clearly separated from the microstructural information. And that kind of, so if I introduce, and anyway, what is universality? What does it mean in this sense? That we use general principles and use only those, then we get the, let's say, consequences that depends only those general principles. If those are independent of microstructure, then will be, let's say, universal in this sense. Okay, and what is also a particular point here that I would like to emphasize, that therefore thermodynamics in principle doesn't require a particulate structure to be obtained. So fields, the second law is expected to be valid for fields as well. Also, in case of idle evolution, okay, we don't expect that some dissipation is at the microstructure. However, second law gives you information on the idle evolution as a kind of marginal dissipation. That will be also another point, and therefore I will use the second law directly for fields. This is the subject of non-equilibrium thermodynamics here. So the challenges and also the benchmarks of the modern thermodynamic theory are the true representation of the second law and the true representation of space-time and objectivity, and those are well-treated long subjects of this field of physics. And what is important, that the second law of thermodynamics is represented by constitutive functions, like the Fourier law of heat conduction, if you can recall it, or the viscosity relations, or the equations of state. And the space-time and objectivity question is also long time treated and appears with the concept of material frame indifference. That is a subject that really incorporates not only simple Galilean transformation, but expects that the material itself, so the material descriptors, the constitutive laws, must be independent of the reference frame in any. And also appears this as a concept of relativistic temperature or variational principles, so it's everywhere because we are dealing with space-time objects. And as a benchmark of the modern theory, then we expect kinetic theory compatibility, and there are many different branches and representations but I don't want to go into the details. But what I wanted to say that if we expect a universal theory somehow, then in principle it can say something about gravity and quantum mechanics, as those are the universal theories in physics. Okay, let me go farther. So how the space-time is represented in this classical way of thinking on thermodynamics? So classical irreversible thermodynamics was developed after the Second World War, so it's not a very old theory, but what we use is, what we apply is the calculation of the entropy production. And the entropy production is the source term of the entropy balance. And the entropy balance is actually looks like in this way, like in the momentum balance previously, that there is entropy flux, and the entropy density, more properly the specific entropy, is more convenient to use in fluid mechanics, so it is this form. And one actually calculated introducing the balance of internal energy and also the, let's say, thermostatic information. I go into the details in the next slide. What is important here that then we derive the inequality and we solve the inequality assuming a linear relation between the different quantities, and then we obtain the required constitutive information that we're substituting back here. There will be the equation that solves the equation, the heat conduction. And what we need to observe here, that there are some general aspects in this derivation, like the space-time, the comoving derivative, and the use of the constitutive state space. I mean, what depends on, so the dependence of Q is expected. And also we introduce entropy density, and the entropy inequality itself is a general aspect if you really agree that no, it is used as a fundamental assumption or fundamental postulate. And we can distinguish between the material properties of kinetic and statistical origin, like the equation of state that energy is proportional to temperature, or that one which we can argue that follows not only, I mean, the particular form of lambda. So this is a consequence of the second law, but what is the expression of the heat conduction coefficient is the consequence of a statistical argument always. And what is also important to understand that entropy inequality is a constrained inequality. I assume that it is valid with the constraints of the balances, so all the other information on the evolution of the system, and also the thermostatic. So I assume that there is an entropy density as well. So these are the aspects of the second law that I introduced. And then the space-time actually appears in a covariant representation. A balance is covariant, Galilei relativistically covariant, and the material properties all are encoded in the second law. So that all what of course they are in particular materials, I can get more information, but here, assuming only that the entropy is increasing, it's enough. And that solution of the inequality looks like very heuristic, and it is, just now, what I presented, but it is more behind. Actually, it can be really understood in a more deeper method. Okay, that's the only picture I will use in the presentation. So I'm just saying that mathematics, a little bit more mathematics follows, which is not maybe not very hard, but sometimes can be tricky. And the relation of mathematics and physics is sensitive. That is the point. And let's go to space-time. Non-relativistic, more properly Galilean relativistic space-time. And let me argue that all the structure previously presented has a background hidden, really looks like hidden space-time representation. One of them is the mentioned co-moving derivative. Now I've written the whole equation in the previous equation in a different form. Now not the momentum balance, but the energy balance. And you see that the time derivative is a partial time derivative, so this is a laboratory frame, what we have here. And what I have it here, that's a transformation of the time derivative to a co-moving, so between the co-moving and laboratory part. And also this is a transformation of the current density vector. This is a vector, normal Galilean transformation looks like. So the distinction between conductive, convective, actually transformation rule. And actually the Galilean 4 vector can be introduced, which is the energy density and energy current density together. And this is meaningful. Also, the constitutive state space, so all the quantities depends on E and the gradient of E, which is a space-like co-vector. So in Galilean relativistic spacetime, one need to distinguish between the linear structures. They are vectors and covectors, and then transform differently if we look from a transformation point of view. And also interesting that the internal energy is normally introduced as the difference of the total energy and the kinetic energy, in a specific representation. And actually, it is also looks like internal energy that moves together with the fluid, and total energy that somehow from the point of view of external observer. Actually, it is also a transformation rule, but to introduce that, you need a more complicated mathematical representation of the whole continuum mechanics. So just looking at this structure from the point of view of really a space-time understanding of space-time, and please little bit think relativistic fluids also, that if you have some background, so energy momentum tensor is expected there. So therefore, from that point of view, it is not a wonder that we have such kind of 4 vectors non-relativistically, but it has some consequences just for not only formally, but from conceptually. So first of all, what is moving when a fluid is moving? It is usually assumed that the movement, so the mass is moving, non-relativistically, but from a relativistic point of view, when we don't have mass, so energy is moving, and or particle density, particles are moving, and we can choose how we define the co-moving system. And this is, let's say, a representation of the observer. Those sometimes called flow frames, they play an important role, especially in non-relativistically, we always very happy with the mass, but otherwise not. So this is one point. The other point I mentioned, that if we want to understand that this is really could be a transformation rule, I mean, the kinetic energy just depends on that. Then we need to introduce some more complicated objects, so 4 tensors, analogous to the 4, but in the Galilean relativistic framework. And but the consequence is that, for example, entropy production will be objective, independent of the observer. And finally, maybe also an interesting remark, that temperature is also a 4 quantity. Temperature is a 4 vector, Galilean relativistic 4 vector, which is scalar only if I move together with the temperature. Therefore, thermodynamics itself defines a reference frame that we can call thermal reference frames, and these are really play important role nowadays in relativistic fluids in heavy ion physics, for example. Okay. Then some remark, what is this Galilean relativistic space-time? It can have a formal mathematical representation, and don't go into the details, but anyway, this is a 4-dimensional affine space where the time is separated because it is absolute. So of course it is non-relativistic or Galilean relativistic, therefore this is a, let's say, a foliation of the affine space actually that is best represented by a separated space-time. And those concepts are present also, for example, in the ideas of Lévy-Leblond and others who dealt with a little bit non-relativistic space-time in more depth. Okay, that's all. How much time I have? Do you know? 20 minutes, yes. Okay, that's great. So the second part, so that's the space-time part of fluid mechanics, which is maybe somehow interesting. And this is a background of a proper evaluation of the entropy principle, because for the entropy principle, I expect the same kind of covariant representation. It is tricky, but also tricky that how could I solve this equation in a mathematically less heuristic manner. And they are the mentioned more sophisticated procedures that starts from mathematical point of view that I simply fix the domain of the various fields, a constitutive domain. So for example, that energy or temperature, or anyway, entropy and the entropy flux and everything, it depends on the energy and the gradient of energy. And you see, this is where this weakly non-local extension plays a role when I start to introduce more derivatives. Here, this is the basic, simple thing. And you see the constraint inequality can be formally applied. So I introduce a Lagrange, more properly, Lagrange-Farkas multiplier. So it's and introduces a constraint. And then, with some calculations, I can deduce some consequences, like in normal non-functional inequalities. For example, I can understand that lambda is the reciprocal temperature. So the multiplier, it's not arbitrary. It belongs to the derivative of the entropy by E. And also, I can deduce that the entropy is independent of the gradient of E in spite of my original assumption. And also, let's say the remaining inequality appears here. Whatever is the calculation, I want to emphasize that I need to fix the constitutive state variables, and if I introduce more derivatives, then I get a more refined theory, and I can apply the thermodynamic constraints differently. And I don't go into the details, so I can deduce the consequences of the second law. Yeah, that I jump, because that's the linear algebraic background, the Minkowski-Farkas, it's a Farkas lemma, essentially, of linear algebra that gives you the conditions. What is interesting here, that thermodynamics, modern thermodynamics can deduce not only relations of some constitutive functions, but restrictions for the evolution equations themselves. And the example is here very simple. Actually, this notation is not very fortunate, but anyway, I have a scalar field evolution equation, and I want to understand what follows, what kind of restrictions should be applied if I assume that it is subject of the second law. So this is not some arbitrary equation from the empirical background, but the second law is required from the first. Of course, I introduce a Lagrange multiplier, Lagrange-Farkas multiplier, and apply the same procedure. That's actually very simple. What I've got is that the entropy will be independent of the gradient of the scalar variable, and f must be proportional to the derivative of the entropy, which is actually then a local ordinary differential equation that I get. However, if I apply a weakly non-local extension, so introduce a higher order space derivative for the sake of simplicity, so the higher order state space is introduced, then I can deduce different consequences. Actually, a more refined evolution calculation, it turns out that entropy is independent of the second derivative, actually. It is not the first. That is a mistake here. So doesn't depend on the second gradient of S. And finally, the entropy inequality appears in this form. So f, the right-hand side of the evolution equation, is proportional to the variational derivative of the entropy. This is probably a little bit surprising, because I didn't use any variational principle here. And actually, then the proper, let's say, linearization gives you the so-called Allen-Kahn equation or Ginzburg-Landau equation, if you like, that is derived usually in a different concept, different framework. Okay, anyway, I wanted to demonstrate that thermodynamics and the second law can be directly applied to deduce some very non-trivial restrictions on the evolution. And there are a lot of weakly non-local extensions in the classical physics. I just mentioned some of them. Let us focus on fluid mechanics. In fluid mechanics, the basic variables are the density, velocity, and the energy density. And the classical Navier-Stokes equation have some structure. And I can say whether the extension, weakly non-local extension in the density, so what kind of theory could we have? And that is the last part of the presentation. It's about Korteweg fluids, because this kind of extension is known for a long time in capillarity. Actually, it was the pupil of van der Waals, Korteweg. It's not the Korteweg-de Vries equation. It's another point that introduced the second gradient of density to the pressure, and assume that the pressure depends on the thermostatic pressure and also several derivatives of the density. Actually, this is a most general isotropic representation. It introduced an isotropic fluid. And these coefficients are density-dependent material parameters. And he started to apply to capillarity, surface tension, but it has very restricted use, because if I combine this constitutive equation with the momentum balance, then I've got an unstable fluid in general, and it was not really used for a long time. Time to time appeared until 1989, so 80 years after Korteweg. The second law restriction was applied to this weakly non-local extension. And then the thermodynamically compatible Korteweg fluids proved to be actually stable and useful for capillarity. From our point of view, as I mentioned, this is clearly a second order extension in gradient of the classical fluid mechanical calculations. And here, the constraints of the entropy inequality are the density, the fundamental balances of mass, momentum, and internal energy or energy. This is actually the same. And therefore, you use the same procedure as before. This is more technical, with the extension that instead of first order derivative, a second order weakly non-local theory is introduced. And what you get is you get several things. That the most important thing, that this form of the entropy production. If you are familiar with it, that is the thermal part that I previously introduced, and this is the mechanical part that normally gives you the viscosity. So it's gradient of the velocity proportional to the dissipative pressure or viscous pressure. This is the viscous pressure. The pressure tensor in the momentum balance, and subtracted the static pressure, a scalar static pressure for an idle gas, and if it is proportional to the gradient of V, then you get the dissipation in the Navier-Stokes equation in an isotropic representation with two coefficients. However, in our case, you get an additional part. And to get this additional part, if the entropy depends on the gradient of the rho. And to get that, the rigorous methods are essential, of course. And if P equals to that, then you get not Euler fluids, but thermodynamically compatible Korteweg fluids. So that part is Euler fluid, so idle perfect fluids, and this part is not. And it turns out that this is also holographic because of thermodynamics. So the gradient of this additional part actually can be written in this form. And if the processes are, let's say, adiabatic or homoentropic, then you get only the classical, I mean, potential representation, where this potential is not the gravitational potential, it has this form. So it can be derived from, of course, related to the entropy, but more convenient to deal with the energy. It has a variational form as a consequence of the derivation. Therefore, the momentum balance can be expressed in this way. So because of thermodynamics, the fluid became holographic. Therefore, there is a transition between the particle and field representation, or let's at least mentally. Of course, those are all fields. And the next question is that whether and under what conditions this phi could be the Bohm potential, which you remember is the depends on the second derivatives and first and second derivatives of rho and rho itself, but in a very particular way. And my point is that actually it is easy to understand and more or less unique how is it follows. Because what I need to assume and understand is the zeroth law of thermodynamics. It's actually essential in quantum physics as well, because I need to separate, let's say, a system from the environment. And in thermodynamics also essential that something which is interacting to the environment, I describe with the temperature which is characteristic to that and not the environment. That's the same question as in the quantum mechanics entanglement, actually. Okay, not the same, but somehow strongly related. So I need to create the separability and understood that how is it go. Of course, I'm in a fluid picture. So therefore, in a fluid picture, let's say there is an internal energy or any function that depends on the sum of the fluid densities. Then usually this is the, let's say, separation of multi-component fluids. But if I want to introduce probabilistic fluids, where this density is not a simple fluid density, which cannot be in quantum mechanics, that quantum mechanics is a probabilistic theory, moreover, not a simple so not a classical probability. Anyway, for any probabilistic theory, it's valid that independent systems are characterized by the multiplied probability density. So therefore, what I expect is that functional representation, so that internal energy must depend on the total fluid probability density, and for independent systems, it must be additively separated. So this is the functional equation I want to solve, and it has a unique solution. Unique is well known for the first part, because this logarithmic function, I mean the logarithm of the two of a product is the sum of the products, and actually this is the gradient of the related to the gradient, square gradient of the logarithm. So it's really easy to understand that it fulfills this differential equation. However, not differential or functional condition. However, it is really interesting that actually this is unique. And this is an energy formula. And if I substitute into the previous representation, I mean substitute here, I mean U, what I've got, is the Bohm potential. So this is a kind of unique consequence of this, so the additivity. And additivity from the point of view of Schrödinger equations means that independent particles can be characterized by independent Schrödinger equations. They are not coupled. Okay, I am to finish, maybe a little bit sooner. But anyway, what I wanted to mention that there is a thermodynamic road from Korteweg fluids, which is a second order weakly non-local extension in density of classical fluids, to quantum mechanics, and there is an intermediate steps which I didn't speak about. That those are superfluids that fulfill some of the conditions, but actually the additivity property is not valid, so they are in a sense normal fluids, but that can be represented by a complex, not wave function, the psi function of Ginzburg or whatever you like. And the conditions that step by step restricted the let's say, modeling framework, theoretical framework, where first the second law and the idolities conditions, so this is a no dissipation conditions, and that and the classical holographic property followed. So this wave-particle duality in this sense was pure consequence of thermodynamics. Second, the additivity and the conservation of vorticity led to, by the way, additivity is necessary for normal superfluids, because that not only the wave complex function representation is important, but also Bohm potential is there, if you think in this way of superfluids. But anyway, that zero vorticity was a assumption in superfluids. Of course, in superfluids, you can see the vortice lines from boundary to boundary, so this is not zero vorticity, but conserved vorticity, so they are really exist. And if you assume that all these constant here, so for example, this term doesn't play a role, and this is somehow related to the Planck constant, which is another point, then you get the Schrödinger equation at least. So this is a very road to very simple quantum mechanical systems, but probably shows the connection to classical systems that is not really straightforward from the point of view of quantum mechanics. And what is finally, what I finally want to remark, that the second law, what the basic assumption was that the second law of thermodynamics is fundamental, is valid also in this, let's say, microscopic world, at least in the marginal case. And of course, I can assume that the dissipation is zero, but still the holographic property is a consequence of that kind of argument. Yeah, and also maybe important to remark that they are real physical systems all along the way. So the Korteweg fluids are real, superfluids are real, and also there are several other examples that fit into this picture, like this pilot wave hydrodynamics. It can be very well represented in this framework. Okay, and going back to the first slide, so I'm really aware of that spin is one of the questions that need to be clarified, and if you can suggest any kind of benchmarks of this set of problems, or are you interested in the background, I'm really happy. What I want to mention that also the analogy version of the reasoning is actually more general than maybe you ever. So for example, there is a hydrodynamic representation of the Dirac equation, also hydrodynamic representation of any quantum field, non-abelian quantum field theory, and also well-known examples of transforming gravity into the hydrodynamic form. So this, I mean, the Einstein equation. So this is a mysterious, looks like mysterious coincidence, the consequence of the, let's say, general form of the balances, but still mind-provoking. And also, you may observe that what I presented here was a way from a very classical system to a quantum system. So this is actually a method of quantization. And I did not speak about general methodology to construct evolution equations. So this really, that was not valid only for the fluids, and this is also maybe weakens or strengthens the methodology that this is a part of. So there are several other examples where this approach through the second law really, let's say, productive, like heat conduction, where we have experimentally, let's say, observed the consequences of that kind of extension. Also interesting, the application to gravity, at least to Newtonian. This is simple. Relativistic is another question. There are some predictions here. And as I mentioned, in case of relativistic dissipative fluids, which with their own problems, is somehow, for example, the thermal reference frame is widely applied nowadays. And there is an experimentally available framework in heavy ion collisions where fluid models are really developed, and and working well for modeling the systems. Okay, and my only figure with the remark that actually I wanted to outline the mathematics, but the mathematics is very simple behind that. No need of Hilbert space representations and projecture measure integrals and let's say sigma lattices, whatever in quantum mechanics. It is misleadingly simple, but it is maybe true. That's why. Okay, thank you for the attention.
Thank you very much. So,
actually,
questions?
Exact.
So, I would have a question about the nature of the Bohmian mechanics, potential, sorry. So you said that it comes, the form of it, from this requirement that if you have two independent probabilistic fluids, the energy should be additive.
Yes.
And so now, how natural is this? Because we have in nature many fluids different of those with the. So if you want to say this is very natural and that's why it comes, basically, that's a very special fluid when compared with all possible fluids that are realized.
That's.
So does it mean that the other fluids violate this condition? What would it be?
That's exactly true. But it comes from the Schrödinger equation. So if you have two particles, you expect that the Schrödinger equation connects them through the potential only. And if it is formulated in fluid form, then that is what follows. So I think this is, I don't know why, but this is the core of quantum mechanics. I mean, the
Put the other way around. Let's take two classical fluids.
Two classical fluids is not for classical fluids. It is this is a model of ideal fluids. So ideal fluids, for ideal fluids, I assume that. So the energy is not connected, or more properly, the equation of state for the energy actually proportional to their partial density. This is.
Does it mean for the two classical fluids we will have some evolution which is similar or the same as
no, because where was it? Yeah. No, because in this case there is no this. So the Bohmian force or pressure is very doesn't introduce a characteristic mass. So it is, let's say, mass scale independent, but introduces a characteristic distance. So these weakly non-local extensions always somehow need to explain or understand this characteristic distance. So this is like in capillary fluids, you see there is a characteristic thickness of the transition of the fluid and non-gas version and so on. And in this case, this is a how to say, the structure of the equations becomes completely different if you introduce that kind of force to the right-hand side of the momentum balance than introducing some normally available external forces. Actually, it is from the point of view of fluid mechanics, the holographic properties is really mysterious because the boundary conditions somehow disappear. And that is related also to the additivity property. So in normal fluid mechanics, we think them as fluid. However, with holographic properties, we may start to think them as particles in a very particular sense. And then this additivity of the Schrödinger equation cannot be transformed 2 steps back to fluid form. Really. Okay, all right.
There's nothing about that. So there is just a function, which is a function of the density, probability density in derivative squared. And I guess at that point it could describe both classical and quantum, where the internal energy depends on these two.
Yes. Yes, yes, yes. But this additivity is not straightforward for normal fluids. Actually, also the another point. I thought that you will ask about logarithm. By the way, if you may know that this is invented in the 70s by Bialinski-Birula, who because more or less the same reasoning that not hydrodynamic form, but with other reasoning. But anyway, that the additivity of the Schrödinger equation can be preserved, introducing that kind of nonlinearity into the Schrödinger form, and that was rejected by Weinberg some months after, with not really convincing, for me, not convincing reasoning. Just somehow he explained that, okay, we introduced that logarithmic term, but we cannot measure it with, I think, chemical reaction, quantum mechanic argument. So it could be measured, and it is too small, cannot be seen. However, nowadays there are several. Seems to be that, for example, in superfluids, where the potential contains the form coming from these, but normally it is a power law development of the interaction potential that is called, let's say, Gross-Pitevsky, Ginzburg, Sobolyev, I don't know the name, and also, but anyway, the logarithmic term somehow turns out to be useful to modeling lambda transition in liquid helium, where the superfluids are valid. So they are. And still, those are additively separable.
I have another question, which I know that you haven't addressed. I mean, it's not one of the blue.
Okay.
It's really like if you want to describe quantum entanglement, and you have then two particles that are not independent in a sense, and then also, if I understand the Bohmian explanation of the relation of inequalities, then the measurement on one particle will influence the potential for another particle, even distantly. So, do you see even the path? How would you do that? Because you don't introduce this ad hoc in kind of mechanics. You say, no, this has a thermodynamical origin and so on. And so I guess that type of argument that you have here, the additivity or generalization of this argument must be then present for two particles.
I have some ideas. Not sure, because this kind of complete transition is I don't know how. So several concepts are somehow not, let's say, up to not straightforward to put. However, for entanglement, in a classical point of view, you have an initial condition also. So you don't have these, as a fluid, let's say, probabilistic or any, and these differential equations in this kind, you need boundary and initial conditions. And if your initial conditions are given for the two particles, and the equations are somehow coupled, maybe through the potential themselves, then the initial conditions entangles the two fluids. As far as I see, this could be produce similar effects than so it's not a common cause. It's a common cause effect, but not from a some conservation law, but from a different point of view.
Well, I guess then this condition would not be satisfied because they are not independent, I guess.
Independent in this sense, but not in the initial conditions are not so independent. Yeah, so this is valid, but still entanglement in this classical sense, what I mentioned, which is not immediately related to quantum mechanical, because I really.
But I guess the total probability distribution would not be a problem.
But I wanted to speak about pure states Schrödinger equation, and so that is another point. And also, by the way, you see, I said that this is an idle fluid, and then I argued that holographic property ends on for idle fluid, but actually there is a whole dissipative background. So Moreover, not only one kind of dissipation, because particle damping of the Bohmian form of the equation is very different than viscosity damping. So it is a kind of new, maybe not new, but nevertheless, from a particle point of view, don't expect it's a viscous fields in quantum mechanics, whatever. So, okay.
No further questions. Let's conclude here. Thanks again.
Thank you for the attention. So.